This video is going to talk about ferromagnetism, and this is covered in chapter 30-7 of the textbook. Alright, so in the last video, we talked about if you have an electron in an atom, well, it's going to have a magnetic moment due to the electron's spin, and also a magnetic moment due to its orbit. Now, for atoms in most materials, so if you look at those and the magnetic moments of all the individual electrons, everything just ends up canceling out. And you wind up with zero net magnetic moments. So this is why most materials aren't naturally magnetic. So because the magnetic moment of the ground or the lowest energy state is zero, since everything ends up canceling out. However, there is a few materials, so they're called ferromagnetic materials, most commonly iron, but also cobalt and nickel, where the ground state actually has a non-zero magnetic moment. And it's actually due to an interesting effect called a spin-orbit coupling, where the magnetic moment from the spin and the orbit are actually coupled together, and they end up lining up, and they don't just cancel out. Alright, so in ferromagnetic materials then, when you have a non-zero magnetic moment, so the magnetic moments of neighboring atoms tend to all align with each other, and you wind up with these regions called domains. And again, this is a fairly large number of atoms, 10 to the 17 to 10 to the 21. Where all the magnetic moments for all those atoms in a single domain tend to line up with each other. So one way to think about it, so you have some sort of a material, it's divided up into these domains, and within a domain, each one of all of these little magnetic moments are all aligned. However, since the domains are all independent of each other, so the magnetization still overall tends to be zero. Right, since when you add up the magnetic moment from all the different domains, if they're all random, then there's still no net magnetization. However, if you apply an external magnetic field, so then what tends to happen is these magnetic moments tend to all align in roughly the same direction. So this is why when you bring a piece of iron next to a magnet, so it sticks to it, because those magnetic domains, magnetic moments in all those domains tend to align. So which gives you a net magnetization. So there's also an interesting effect called the Curie temperature, where eventually if the temperature rises enough, well, the domains will actually de-align and there will be no net magnetization. So you heat something up to high temperatures and you actually lose the magnetization.